So the layers of information begin to accumulate. Locating areas with suitable characteristics for underground disposal is the job of geologists like Maxwell Blanchard of the U.S. Department of Energy, Nevada Operations Office.
By studying surface and subsurface geology, we found several sites around the country where the rock is favorable to the deep burial concept. Salt beds, for example, are an excellent rock, and granite has excellent possibilities as well as basalt and tuff.
Once a suitable rock has been located, other Earth scientists determine the feasibility of a site in terms of other factors. One of these is geologic stability. Jerry Frazier is a seismologist for Science Applications International.
Recordings of minute seismic signals enable us to see inside the Earth and map geologic formations in much the same way the medical profession uses sonograms to see inside the human body. Seismic investigations of a site allow us to make confident predictions about its future behavior. We're looking for sites that haven't been affected by earthquakes or volcanoes for millions of years, for we believe these sites will be stable for a long time to come.
As potential disposal sites are identified, local studies become more specific. Hydrologist Roy Gephardt of Rockwell International.
Of major importance in selecting sites for waste burial is an understanding of water movement beneath the land's surface. This water is called groundwater. We want to find those sites where we can understand the groundwater environment, where we can answer the major questions concerning where the groundwater comes from, how it moves through the rocks, and where it will be moving to. We are also looking at the history of groundwater movement at the proposed repository sites, and then using this information to project future groundwater motion in and around the repository. Our goal in conducting these groundwater studies is to identify that site or those sites that have the natural rock properties to keep the waste buried deep underground until it becomes harmless to man and the environment.
Beds of rock salt, for example, are one type of formation being investigated. Geologist Mike Beathard, Bechtel Civil and Minerals Incorporated.
We are at the WIP site, which stands for Waste Isolation Pilot Plant. The WIP site is located in the Salado Formation. It's a 3,000-foot thick layer of bedded salt. We are approximately in the middle of that layer of salt. There isn't any real groundwater problem here because the salt has been here for, well, the rock formation here is 225 million years old, and all that time it has not been dissolved by groundwater. Gives you a pretty good indication of the fact that there is no water at this level.
From field research data, engineers now generate computer models that project the long-term effects of natural forces on various rock formations in order to determine those best suited to become repository sites.
Just as computer models are used to predict geologic stresses, we also use computer models to predict the outcome of severe transportation accidents, so we can design the packages or casts to withstand them. Here at Sandia National Laboratories in New Mexico, radioactive waste transportation packages are thoroughly evaluated and shown to be one of the safest approaches to cargo handling ever devised. These scale model and full-scale tests are used to verify what our computers have already predicted.
5, 4, 3, 2, 1, 0.
The casks survived these tests, as our computer models predicted, with their ability to contain their contents intact. Thousands of safe shipments of spent nuclear fuel have been handled and delivered without a single accident, resulting in a release of radiation that endangered the public. We can now say with certainty that under normal conditions, or even in the case of an accident, we are capable of safely and securely handling the transportation of spent fuel from power plants to a repository.
Based upon the findings of all the various experts in the field, computer models, research, test results, and predictions, we are developing detailed and comprehensive plans for the deep disposal of nuclear waste in repositories in stable rock formations. To give you some idea of the scale we are talking about, the depth of the repository would be up to 3 times the height of the Empire State Building. Yet the volume of waste to be disposed of is very small. In fact, all the nuclear electricity ever generated in the U.S. through the end of this century will produce spent fuel equivalent in volume to a cube less than 100 feet on a side.
The layers of information now become a plan. The basic concept for a nuclear waste repository is this. Shipments of spent fuel will arrive at the repository either directly from a nuclear power plant or in consolidated form from an intermediate storage and packaging facility. They will be received at an above-ground service building. There, the spent fuel rods will be removed from the shipping cask and placed in a disposal canister. These canisters and containers have undergone extensive tests to assess the effects of heat, radiation, and groundwater at the proposed site. The disposal canister may then be placed inside another container, an overpack, all by remote control. The container is then sealed and inspected. And the entire package is lowered down a repository shaft or ramp. The shaft, about 1/4 to a half mile deep, is lined with a material such as steel or concrete. Deep inside the repository, a transportation vehicle receives the waste package, then carries it to an emplacement tunnel or drift. Final destination for the waste is a hole drilled in the drift floor or wall. Materials such as clay, sand, bentonite, zeolite, or crushed rock from the repository may be filled into the spaces between the canister and the surrounding rock. Then a cap is fitted over the waste package and the hole filled to floor level. When all the holes in a drift are filled, the drift may be backfilled. Ultimately, the shafts will be plugged, backfilled, and sealed. The depth at which to place the waste is carefully chosen to minimize the amount of groundwater present. But if any groundwater were ever to move through the rock toward the waste package, its progress would be slowed and its chemistry altered by the special backfill. Additional protection against water is offered by the corrosion-resistant overpack and canister, by the metal cladding around the fuel, and finally by the solid fuel pellets themselves. This series of obstacles is called the multiple engineered barrier approach. It ensures that the total system would continue to function even if one or several of the barriers failed to work. And this entire process of multi-barrier protection also works in reverse to assure the safe containment of radioactive waste.